no class on Monday, no class on Friday of next week. Monday is the university is giving you a day off. Friday I'm giving you a day off. I want to make sure this, I get proper credit for this. Class and homework as usual on Wednesday. I'm not just sloughing off. I'm going to a conference. I have to give a talk on Friday. So after that, there will be a regular schedule, Monday, Wednesday, Friday. Please use the time, Monday and Friday, to study the homework solutions. We're introducing a lot of mathematical concepts here. Practice them. Study the solutions carefully. Make good use of the time. I still own your time, right? So, especially on Friday, even though we're not having class during the lecture, you still need to study. Okay, and so we're going to go over today's homework. There's solutions here, for the questions from the textbook, but I'm going to go over the questions here for the electric field. Okay, so we're beginning to study the empiriometric study of the electrostatic fields. So what are the conditions for an electrostatic field? Or the electrostatic approximation might be another way of saying it, because this is a special case of an electric field. So what would be the conditions that make it static?
Charges don't move.
Yeah, charges don't move. Nobody moves, right? And charges don't move. Observer doesn't move. We're putting things in a particular place. We don't want anything to move. We did that a lot last term. What were some of the approximations that we made? We kind of froze something. We kind of discarded consideration and then come back to it later. So what were examples last term where we did that? Mr. Sun.
Collisions.
What was the approximation there?
It was, we would take out things like air resistance.
Yeah, okay. So in locomotion, we got rid of friction first, and we studied locomotion in the absence of friction. Then we came and considered what would happen if friction were put back in. We understood friction as a force. We considered no rolling, right? Just sliding, no rolling. Everybody had to slide, couldn't roll until we got to chapter 7, then you could roll. Okay, so the same thing is happening here. We're going to consider just put the charges in place, and we're just going to study that. That's the first step. So the electrostatic approximation. In the electrostatic approximation, we're going to consider putting a charge, Q, at some location, and we want to find over here at some other location, what is the electric field over here? Generated in the plana by that charged body, right? When I say a charge, what I mean, I'm focusing on a substance, a massive body with charge. When I'm going to use shorthand, I'm going to say charge. But, of course, charge does not exist by itself. It's a property of a massive substance. And so it's always, but I just refer to it shorthand as charge. So remember, this is what I mean when I say charge. I mean a charged massive body. Okay, so now the general expression for this electric field, I want to set it up in a general vector set up here. So I'm going to have an origin for my coordinate system. And the location of the charge I'm going to call R prime. That's the vector going from the origin to the charge. And also the location where I want to know my electric field, what the electric field is, that location. That location is called R. And I need to know the relation, the relative displacement from the charge to that location. Okay, and I'm going to call that script R. And that is, of course, then the difference between R and R prime. Okay, so now this vector script R, of course, has a magnitude and direction. And so the magnitude of script R I'm also going to write just as the script R with no vector over it, just as usual. And then there's also a unit vector, so I could rewrite that script R as the magnitude of its magnitude times its direction. So R hat is going to be the vector divided by its magnitude, as usual. Okay, now let's write this in Cartesian form. The Cartesian form, so all this was done without reference to a Cartesian coordinate system, but in a Cartesian coordinate system we choose directions x hat, y hat, z hat, and then the coordinates are going to be called x, y, z, and also x prime, y prime, z prime. And then script r in Cartesian form is x minus x prime in the x direction plus y minus y prime in the y hat direction and z minus z prime in the z direction. Okay, and then the magnitude of r is going to be, the script r is the sum of the squares of the components. This looks kind of complicated here, but it's really going to be helpful to get all of this down and refer to it later. So it's the square root of the sum of the squares. And then script r hat would be, of course, take that vector and divide by its magnitude. So I'm not going to, I guess we might as well, for completeness, go ahead and write it out here. Divided by the sum of the squares of the differences. Square root of the sum of the squares. Okay. So a little bit of math here is going to be really helpful for us in dealing with this. Okay, so the general expression for the electric field generated by that charge, and I'm going to write this in CGS, can be written either like this or also like this. The latter form is a little bit more convenient. And so if I write all of this out in my Cartesian form, this is going to be x minus x prime, x hat, plus y minus y prime, y hat, plus z minus z prime, z hat. And then I divide by the cube of the length, and the length is a square root, right? So I'm going to take the square root of this, but I'm going to cube it. So in the denominator there I have that thing to the 3 halves power, God bless, because it's the sum of the squares, I got to take the square root, but then I cube it. Okay, that's a general result, and I want you to have that in your mind. That's a very general result. You ought to be able to, in fact, memorize that. It looks a little complicated, but it isn't once you understand the structure of it. And we'll keep coming back to that over and over and over again while we study electrostatics. And in fact, the same sort of mathematics is going to be used to describe the vector fields in general, the electric and magnetic fields of charges once we allow them to start moving and so forth. So this is all going to be the basis of our description of these fields, mathematical description of these fields. Okay, now let's take a special case. Let's put Q at the origin. The charge is at the origin, and in that case, x prime, y prime, z prime are all equal to 0, right? Remember, the prime refers to where the charge is. The unprimed is where we want to know the field. So in that special case, then, we set the primes equal to 0 in that more general expression. And this can also be written as r over r cubed, the vector r over r cubed, which could also be written as r hat over r squared. Okay, so you can see now what we've done is just express Coulomb's law. The strength of the electric field is proportional to the charge. It's generating the active charge. It's generating the electric field. It's inversely proportional to the square of the distance, and it points radially outward. And that more general expression that we have simply extends that expression to where the charge is not at the origin, so we can have charge somewhere else. Okay, so that's the general expression. That's the more specific expression for Coulomb's law, where we're considering the origin is placed where the charge is. But we want this more general one because we want to have more than one charge. We want to put charges in different places. And so then when we have multiple charges at different location, the net electric field is a superposition of the contributions from individual charges. And when I say superposition, I mean a vector sum. Right? That's expressed empiriometrically that the electric field of the net electric field might be the electric field generated by one charge, and then the electric field generated by another charge at a different place. We just superimpose the vector fields, and that gives us the net electric field. The plana response of the plana is to in that fashion. Okay, so now in the homework you were given a very simple step to begin with. Q is at the origin, and you want to know the electric field at a distance d along the x-axis, so this vector is just dx hat. So now the electric field then is going to be Q over d squared x hat. The electric field points outward from the charge. The charge is here at the origin, and we're some distance d. Then the electric field points that way, and it's of strength Q over d squared. Okay, that's the first problem. Now let's Q. We put now a charge which is twice as big, negative, in fact, so it's the opposite type, also still at the origin, but we want to look along the y-axis here, twice the distance away. What is the net electric field? Well, the electric field is now clearly going to be, because it's a negative, the opposite charge, it will be in the opposite direction. So the electric field would be down here, and it's twice the distance away, but the charge is twice. So the net result is it's minus 2q, but I take the square of the distance like that. So the net result is that the electric field is half of the strength of the previous problem, because it's a combination, twice as much charge, but it's twice as far away. So because the distance, the dependence on the distance is squared, ends up being weaker electric field in strength, pointing in along the y direction. Okay, so now we're going to get into some of the problems that you're going to do for Wednesday. So the first one is just the general place. We put Q at the origin, and we want to write what is the general case. We want R is some general location, x, y, z. Putting the directions in here specifically like that, keeping to the notation. We want to know what is E of that at that location. So let me write it this way. What is E at that place? Okay, well that's really what we've written, right? The electric field here is then Q, x hat plus y hat plus z hat over sum of the squares. What's the power here? 3 halves. Okay, now you're to make a sketch this in the xy plane. In other words, z is 0, right? So what does that look like? What does that electric field look like? Now we could write it, remember, as r hat over r squared. That may make it a little easier in terms of sketching it, where r is the vector in the plane. So we want to make a a field plot, a vector field plot sketch. So we're drawing arrows. And the way to do that is just pick sample positions and start figuring out where the arrow points. And then remember the vector has both magnitude and direction. So if we're along the x-axis, what is the direction of the electric field?
Positive x.
Positive x. And how does it depend on the distance from the origin?
It gets smaller as it moves away.
That's right. And it gets smaller like the square of the distance. So it's dropping off pretty quickly. So, and in fact, we really can't draw the field close to the charge because the arrows would be getting enormous. So we stop, we kind of exclude a region around the charge because it would be really impossible for us to draw these enormous vectors on this. So you have to really pick a region. So you're going to kind of exclude this region because that would be very hard to draw the field. But you can, but now out here it's going to be pretty strong, and then twice that distance away it's going to be 1/4 of that strength, right? And then the same thing along the y-axis. It's pretty big here. It's 1/4 of the strength. Pretty big here. It gets weaker. Pretty big here. It gets weaker. So with just a little bit of work, you can get a pretty good idea, and you'll get accustomed to drawing these things. It won't take long for you to figure out how to sketch these. And that's what I'm looking for in a sketch. It's not real precise, but it's to show that you can demonstrate to yourself and to others that what this field looks like. And so this sketch means that I could pick some position here away from that charge, and I would know what the nature of the planet is in terms of the electric field that exists in the planet. And that means if I were to put a test charge here, I would know what direction the force would be on that test charge. The field exists even without the test charge, but if I were to bring in another charge, a second charge, and put it someplace in this field, the force is either going to be away or towards, depending on whether it's the same type or the opposite type. Okay? So the force is going to be just directly proportional to the field. And he goes through a discussion in the text, which is worth, of course, pay attention to, of course, the distinction between active and passive charge. We did that before when we were talking about active and passive masses. And of course, the primary meaning of mass related to inertial, what's often called the inertial mass, which in other words is what is the resistance to the impetus. That's the primary meaning of mass. There isn't something like that in charge, right? We don't have charges not directly related that way to impetus like mass is. But charge, nonetheless, is a property of a massive substance that can alter the plano surrounding it, and then the passive charge is what receives the field. The effect of the field is plano produces a force, and so forth. Okay, and again, just as happened in the empiriometric form of Newton's law of gravity, we can drop the distinction between active and passive charge because they seem to be empiriometrically you can treat them as though they were the same number, and therefore drop the distinction. But in principle, the concept is different, and the physical principle is different. Okay. Okay. So now, go on to the next. The next problem is that what is the general expression for the electric field if we place a charge Q at some particular point? Here's the answer to that, right? This is the general expression. And then you do a few simple cases, but here's one I want to work with you here, so that you can see where this is going. Let's suppose we put two charges of opposite type. Let's put a plus Q, a distance d along the y-axis. Now let's put an opposite charge across the origin. This is called a dipole. In fact, it's an electric dipole because, of course, we're just dealing with charges here. So it's an electric, and it's a stationary. So it's an electrostatic dipole. It's just we're putting the charges there. We just want to see what the field looks like. So now we want to know at some position r, what is the electric field over here? generated by these two charges. And so we're going to examine the dipole field. And also we want to have an understanding. We're going to take a limit of this dipole field, which is going to be considered in two different extremes, near field and far field. Those terms refer to how close we are to the dipole. Actually, you know what? I need to put, no, that's okay. That's fine. Never mind. That's fine. Okay. So, near field and far field are distinguished. There's only one length scale in this problem. What is the length scale that's set up by the charges we put in there? It's the distance between the charges, right? And so the length of R is going to be measured relative to that. And so near field means that the magnitude of R is on the order or less than D. It's close. You're close into the dipole. So you can see the two charges separate from each other. Far field means that R is much, much greater than D. You're really far away compared to the dipole separation. Now, let's look at the principle of superposition here. When we have this, I'm going to draw the same thing again here. Here are the two charges, plus Q, minus Q, and their separation between them is 2D here. And let's look along this axis. I'm going to call this, I think I already chosen that, the y-axis here, and this is the x-axis. Okay. Let's look along the x-axis. So on the line that is perpendicular to the dipole. It goes right through the origin. So it's a very symmetric point here. And let's consider what the electric field looks like here. So we get two contributions to the electric field. Each of these charges generates an electric field in the plane, and the superposition is what is the net electric field that any third charge would experience if we put a third charge here. So now we need to look at this. Here is the vector connecting the charge to the point, and so there's going to be an electric field which is in this direction, right? And the magnitude, this distance here, is going to be x squared plus d squared square root. That's the distance of that hypotenuse. Now, what does the electric field generated by the other charge look like?
Same magnitude towards it.
Same magnitude because it's the same distance, but it's towards it. So there's an electric field vector this way. It has the same magnitude, but not quite opposite, right? They're almost opposite, but not quite. And if I add those two vectors together, let's see, here, go to my pens. So I want a third color. There must be a third color here. All right, well, I have to remember how to do this. So the net field is going to be downward, the net electric field, and not very strong, because those two fields are almost canceling each other. Not quite, almost. Okay, and then on the other side of the dipole it's the same. It's symmetric, left and right. Okay, and if x gets really far away, in fact, that electric field drops very quickly. Now, why is that? Why should the electric field be dropping very quickly? We say from a single charge, it's dropping off like 1 over the square of the distance. Now, in this case, we're going to expect it to drop off faster because I have opposite charges there. If I get really far away, it looks like there's no net charge in this region. So the electric field ought to be dropping off very quickly. So you're going to calculate the far field of the electric dipole. How fast does the electric dipole field drop off? We know, so the first situation where you have a bare charge, just one bare charge, that's called a monopole. Now we have two opposite charges, that's called a dipole. So if we go back to that problem we started off, this would be called the monopole, because it's a single charge. Now we've created a dipole, and the dipole field will drop off faster than the monopole field. The monopole field drops off like 1 over the square of the distance. The dipole field will be faster. You're going to discover what that is. Taylor series, right? Seems like a Taylor series is coming here because you have the size of the dipole d over the distance r is a small is a small number. The ratio is very small. So you could do a Taylor series, and in fact that would be one way to go about doing it. Okay, would be to write a Taylor series. Okay, so to that end, let's look at this x squared plus d squared to the 1/2. And if we want, in this case, x is going to be much, much greater than d for the far field. If we're looking at the far field. So we would want to factor, let's take x squared out here, so we have d squared over x squared here, like this, and we take the square root. And since x is positive, we can just pull that out. Okay, and now d over x is very small. You remember, what is the Taylor series of the square root of 1 plus something small? It's 1 plus 1/2 of the something small. That's the first order term in the Taylor series. Okay. But remember, what we have here in the denominator is the thing to the 3/2. The 3/2 down there. So it's going to be a little bit different. You can do this in a couple stages. You can take this cube of what we have here. Or you could look at the form of the Taylor series of the 3/2. Either way, this is the approximation that you will use from the denominator. Remember, this is in the denominator, so 1 over x squared plus d squared to the 3/2 is going to be then approximately equal to 1 over x cubed, 1 plus 3/2 of d squared over x squared. Okay, so now we've got the 1 over x cubed. That's straightforward. We have this 1 over 3/2, so it's 1 over 1 plus something small. Do you remember, what is the approximation of 1 over 1 plus something small? That's 1 minus the small thing. Okay, so in other words, you're going to use this approximation. I see a typo in the homework. I think I say any point y on the x-axis. That doesn't make any sense, of course. Any point x on the x-axis. I see a typo in my homework. I'll try to fix this assignment, but in case you are working with an older copy, problem E and problem F have a typo in them. It says, determine the electric field vector at any point y on the x-axis. That's a typo. It should be any point x on the x-axis. Okay. Okay, so that will help you to determine what the dipole electric field looks like, at least on that line. The dipole field at general points is pretty complicated, but you could do it the straightforward way. Just proceed in this and use this approximation that I've given you here, except that you also have to take into account the y-coordinate of the point. So it's basically the same idea, but it's a little more complicated. Okay, so you're only going for the homework. Just look at the dipole field along that line that separates the two charges. Now, if you were to do the same problem, let's go back. What if the two charges were the same? What if they were not opposite but the same? Okay, so let's look at that problem. We have plus q and plus q. A distance 2d straddling the x-axis like that. And let's look at, of course, what we expect the fields to look like. Now they're going to have the contributions are of the same strength, but now they're both pointing in the same, almost the same direction. And so the superposition is now pointed straight along the x-axis, not the y-axis like it was before, straight along the x-axis, and it's quite strong. So this is not a dipole, this is actually approaching the monopole field. In fact, it should look like the field generated by a charge 2q at the origin, because now these two fields are almost in the same direction. They're going to superimpose, and the farther away you get, the closer those two vectors get. So now you get a field which is twice as strong as the field from one charge by itself. And the separation here becomes negligible between them. So the farther away you get from these charges, the less important is their separation between each other. They're all the same charge. Okay. All right, following this, here's another exercise. You have 4 charges plus q at A, plus q at A, minus A, negative q at minus A, negative q at negative A, negative A. 4 charges, 2 positive, 2 negative. What is the electric field at the origin? These guys are located on the corners of a tetrahedron that surrounds. No, it's not 0.
Oh, wait.
No, it's not 0. Okay, so these guys are on the. I think you're going to have to probably work it out. You might be able to figure it out, but it's not 0. So there's 2 plus and 2 minus like this, and so there's going to be. I think you pretty much kind of intuit the direction of it by looking at it, because it's, remember, it's going to be repelled by positive charges and attracted by negative charges. That positive charge would be, so and you're looking right here at the center. So there's a lot of symmetry in this, but it's enough complicated enough to make it an interesting exercise. Okay. Any questions so far about that?
See the coordinates again?
Yeah. It's in the assignment sheet, of course. Yeah. I'm just going over what's written down in the assignment sheet. You know, you can see from this, if I've drawn it correctly here, yeah, this is not quite right the way I've drawn it. Anyway, this I guess would be the way I've drawn it. This would be the x-axis, the way I've drawn it. Okay, so it looks like the electric field will be along the negative x-axis. But I want you to go through the process of applying this general formula. Now, I've done kind of the opposite here. The charges are not at the origin, and you want to know the electric field at the origin. So x, y, and z are 0 now. X prime, y prime, z prime are those 4 combinations, and the charges, 2 of the charges are positive, 2 are negative. It's a little exercise in vector addition, figuring out what the vectors are and then adding them together. Find out what the net is. Okay.
Is that 2D drawing? Or?
Well, it's supposed to be in 3 dimensions. A tetrahedron, I don't know, it's kind of hard for me to hold my hands, has 2 parallel lines that, not 2 parallel lines, but they're 2 lines like this. That would be the top and bottom edges of the tetrahedron. Each corner of the tetrahedron has 3 lines connecting it to the 3 neighbors, the 3 other charges. All the lines are the same length, and these 3 form the same angle with each other. So that's a tetrahedron. But, and you could use the coordinates there to figure out the geometry more carefully in your head. It's hard for me to draw it, except I've done a pretty good job there. Each face of the tetrahedron is an equilateral triangle, and there are 4 faces of the tetrahedron. So you take 4 equilateral triangles and stick them together, and that's the surface of the tetrahedron. Okay. And the charges are on the corners of the tetrahedron. Okay, now, given the force that would be present, we can also write the potential energy. So the electric field, so if we have let's start off with a charge at the origin, Q at the origin. The electric field generated then is Q r hat over r squared. And the force on another charge, let's call it Q1, let's put Q1 at the origin, and then we bring up Q2 and put it at some distance, a vector r from it. So Q2 is at r. The force on 2, because of 1, is the product Q2, Q1, r hat over r squared. Okay, now how do we calculate the potential energy of this arrangement? Now, if the charges are the same type, then this will be a repulsive force, trying to push them away. If they're of the opposite type, this force will be attractive. Okay, so let's consider the case where they're the same type. It's a repulsive force. And I'm going to put my reference point at infinity because the force there is going to 0 very quickly, 1 over the square of the distance. So let me choose as a reference point arbitrarily far away. Of course, an infinite thing is a limit, so I'm going to take the limit as that reference point goes far away. And now I'm going to bring in this charge, and it's experiencing a repulsive force the whole time that's increasing in strength. And now what is the work done by that electrostatic force? Is it positive or negative?
Negative.
It's negative because I'm displacing opposite to the force. I'm doing negative work. So that means the potential energy is going up. Okay, remember now, and so I'm integrating. So the work done is going to be the integral of f dot dr from infinity to some point r. And because they're in opposite directions, so dr is r hat, so I get q2, q1, integral from infinity to r, dr over r squared. Okay, and so I get q2, q1 over r when I do the limits and evaluate. And to check that, I'm sorry, that work would be negative, excuse me, I get the negative. Yes, there's a negative sign when I do the integral. 1 over r squared gives me a negative 1 over r. So the potential energy at r is then positive, Q1, Q2 over r. The potential energy of 2 bodies experiencing a repulsion is that. Now there's also, when I bring up this charge, there's also force acting on the original body. The first charge is experiencing a force, because as I'm bringing up this charge, there's a force pushing on this one, but there's no displacement. I'm not allowing it to move, so there's no work done on that one. So for the total potential energy of the system, the only work done, the way I've done it here, is that first one. Okay, now I could do it more symmetrically. I could bring them together. I find that the total potential energy of the system is the same. If I do it, bring them together. Okay, so either way I do it, the potential energy is the same as that. And now I want to take the gradient. The force is the negative gradient of this. And that will give me, when I take the gradient, there we go. Okay, so this is the repulsive force. Here's the negative gradient of that. Okay, so now in general, then, if I have a collection of bodies, suppose I have 3 charges, Q1, Q2, Q3. I want to know the total potential energy. of that. Remember, the potential energy for a conservative force is independent of path, and that includes paths involving multiple bodies. It doesn't matter how I bring all these bodies together, but my point of reference is to move them all separate from each other. The point of reference is separate all these charges from each other so that they're not close together, and now I can bring in one at a time, or bring them all three in at the same time, or two first, and then another. Doesn't matter how I do that. It's a conservative force, and so the work done is independent of how I arrange it, which is path in a general way, right? Not just path of an individual body, but how I'm assembling it. Okay? So, and in fact, because the forces are superposed, the work done is the sum of the work done by individual forces. So in fact, the total potential energy is obtained by taking the sum of the potential energy of each pair. So the potential energy of 1 with 2, the potential energy of 2 with 3, and the potential energy of 3 with 1. And so this would be Q1, Q2 divided by the distance between 1 and 2, plus Q2, Q3 divided by the distance between 2 and 3, and Q3, Q1 divided by the distance. Okay, and that gives me the total potential energy. Okay, and you're going to have a problem where you go back to this arrangement of 4 charges up here. You're going to find the total potential energy of that system. You've got 4 charges. You brought them together from far apart. They're all started off at infinity. You bring them together. What is the total potential energy contained in this system? No. Okay. All right. Now, what's related to this? What's related to the electric field? The electric field. What is an electric field? Which you should have read about. What is an electric field? Now, on the blackboard, there's a shorthand version. If you look in the cover of the textbook, it will give you the explanation, right? Just like what is impetus, what is momentum, what is mass, what is force. We've got what is plana, and we've got what is an electric field. So Mr. McKenna has his book open. Would you please read loudly so the microphone can pick it up? What is the electric field?
All right. Electric field is a power or ability, quality of the plana, caused in it by a body with a charge. The relation between the measure of the strength and direction of the electric field, the vector E, the measure of the distance r, and the measure of charge is causing it is the vector E equals Q1 over r squared r hat. The relation of the measure of the force caused on a charge of measure Q2 receiving the action of the field of the first charge is written F, or the vector F, equals Q2, the vector E. The strength of the electric field in a given Cartesian direction caused at a given point in the plana by one source adds linearly with the strength caused by another source. Positive and negative charges act against each other and thus add as well. This principle of superposition is written as a fairly long integral.
Yeah.
Would you like me to read that one?
No, it's all right.
Okay. Where rho is the static charge density.
Yeah, we'll talk about rho here in a little bit. What is meant by the charge density. Okay, everybody's got that memorized? Right? You can repeat it? Yeah, okay. So I have short version of this. Now that's in the blackboard, and that's what I want you to memorize. Of course, what I want you to understand is everything that's in that. I want you to understand everything that is said there. But I want you to be able to regurgitate on a test and for yourself the short version that's on Blackboard. Now, the problem with the short version is this. The short version focuses on that first sentence. What is that first sentence? Read it again, please.
Electric field is a power or ability of the plana caused in it by a body with a charge.
Yeah. Okay, so again, when you have a question, what is, you start with the most generic. It's a property. It's not a substance. Electric field is not a substance. It's a property. What's it a property of? The plana. And what kind of property? It's a quality. It's not a quantity. It's a quality. But like other qualities, we can do a process of measuring because it varies in intensity and also direction. And so we can make a measurement of this thing and write it analogically as in terms of a number in an equation. We can start relating, and we have the symbolic system, and we have the imperiometric. Here we go, right? We're all set. Now we can start calculating things. Okay. Now the problem with just memorizing that first sentence is the full definition has the imperiometric integrated in it, right? There's the equation. Here's the electric field strength. And this is the force that's caused in a second body. And all of that's in the definition. Excuse me a second here. This is my reminder. So the proper definition has the imperiometric integrated into it. The challenge for me to teaching you this course, and I'm sure I'm going to get better at it as time goes on, is to teach you all of it integrated together. I don't want you in your mind to be separating the explanation from the imperiometric. I don't want it to be like something that's kind of added on. Here are the equations. Well, you also have to memorize these things, right? That's wrong. If I've done that to you, I'm trying to not do that to you. I want it to all be integrated. So the principled understanding of how what the electric field is and how the strength depends on distance and all that sort of stuff is expressed mathematically, and it's integrated, and it's a whole. Okay, so that's the problem. So I've given you these short versions, but the problem is what I just told you, and so I'm working against myself by giving you a short version, right? So, but what I want you to do is to study the full version that's in the text. It's nicely summarized. The basic physics of electric field is summarized right there. So there's a famous series of textbooks by Richard Feynman, introductory physics textbook called the Feynman Lectures on Physics, where he taught freshman physics, freshman at Caltech for a couple of years, I think it was, and the lectures were all recorded and transcribed, and and he had notes, and how many of you have read that? Okay. Yeah, it wasn't particularly successful, and that was this. There were a number of reasons for that. One is my own personal experience. You go to a lecture by Feynman, and he's explaining things, and he's got his arms waving. He's got all these images that he's conveying to you and expressing things, and it's like the universe is opening up. Right here, it's just like, wow, this is great. And then you go home and you try to work a homework problem, and it just kind of evaporates because you're not really thinking like Feynman does, and so it just doesn't quite work. And I think a lot of people had that experience. So as an introductory physics textbook, it doesn't work very well for most students. But a lot of physicists, after they've learned the basic stuff, they love to go read this because he's got such a different way of looking at things. And so it really is, after you go through this course, go to the Feynman introductory lectures. His volume on electricity and magnetism is very interesting because he says, and I'll bring you the quote, I don't have it with me right now, I'll bring it next time. He doesn't know what an electric field is. He can't answer this question. I don't know what an electric field is. I've thought about it a lot and I can't explain it. This is what he says. And he says, I can give you the equations. I have in my mind, he says, when I talk about electric and magnetic fields, I have wavy lines with arrows that I draw on them, and other wavy lines like this, and other arrows, and I write E and B, and he says, I have these images in my mind. He said, this is what I think when I think electric and magnetic field. He said, I don't know what it is. I confuse the symbols with the thing itself. And so he's confusing the math and the symbols and these images with the physical attributes. And he's confused those. And he realizes that, and he's unhappy with that. But he doesn't know what to do. Right? And that was a challenge for him all of his life, all of his career. He always said, if you really understand something, you should be able to explain it in simple terms. And if you can't do that, you don't understand it. And he was always unhappy when there were things that he couldn't explain in simple terms. He told a story about he went away to grad school and comes back with a PhD in physics from Princeton. And his dad asks him, okay, so there's an atom there, right, that can emit light. He said, is the light inside the atom before it comes out? And he's stumped. He doesn't know how to answer the question, and his father's very disappointed. You know, all that learning you've done, you got your PhD in physics, you can't answer a simple question like that. And he was very disappointed in himself that he disappointed his dad. He couldn't answer this question. And that's the way he was, and so he was felt that way about this subject, the electric field. And that's, again, for this textbook, I think really plows ground that has been waiting to be plowed and is really accomplished. This is a real accomplishment to think about this stuff. The electric field is quite clearly a property of the plana, and it's very orderly progression. But because, I'm sorry, I'm interrupting myself here. It's really exciting to find a textbook like this that really doesn't give up on the intelligibility of nature. Nature is intelligible and we can understand it, right? And it doesn't just start writing equations and give up understanding at that point. Okay, so understand these short forms in the covers there. Read them and study them. I'm not going to expect you to be able to write the whole thing down on a test, but I'll give you the short version. But the problem is that this integration with the imperiometric, it's one thing, right? The imperiometric builds its context from the fuller understanding, the fuller physics. And it's the fuller physics that I want you to learn. Okay, so we'll see you on Wednesday. Yes, sir, Mr. Friedel.
This is the calculation.